Hello, Christian Krummenhoft from Liverpool. I've had a lot of questions recently on how do we model monopiles, and I'm going to give an example of monopile modeling with respect to ultimate capacity in the following here. So I am going to use some real data, sort of more or less real, from this paper here, Byrne and a lot of other people on the so-called PISA design method for offshore wind turbine monopiles. And so as part of this PISA project, a lot of tests were done on monopiles of different diameter, different penetration, and so on. And so I'm going to use some of the data from the test, the data from the Cowden test site. That's this one here, just to sort of make it a bit more realistic. So let's get started. And a monopile is a hollow cylinder you stick into the ground, so that's what we're going to do. But and I'll go for something similar to what is shown here, a depth of the soil domain of 14 meters, and then I will have a pile of 10 meters, say, and let's make it a diameter of 1 meter. I think that's similar to one of the piles that was tested. But let's define the soil domain first, and so I am going to basically use an end prism, something like 20 sides, and if we are at 10 meters, then probably a diameter of something like 30 meters, or radius of something like 30 meters is more than enough. So let's make that 30 meters, and a height then of 14 meters, and I'm going to make it 14 meters downwards, like that. And that was probably even too much, but never mind. And then the monopile, and I'm going to have it 10 meters below ground and 10 meters above ground. So how many sides in that monopile? We can take another 20, make it 24, and then the position is, so here we're at 0, 0, 0, so we want to be at 0, 0, 10. That's the top, radius of 1, and a height of minus 20. So here we are. Turn this grid off. So here we are. This is our monopile. And I have made this domain far too large, so I'll just actually correct that. Was it 20, 0, 0, 0, and then radius of 20 meters should be more than enough, and a height of minus 14. Like that. That looks more reasonable. Okay, and then we had this sand layer down here as well. I don't think that's going to influence things very much, but just for the sake of doing everything by the book, let's define this sand layer, a radius of 20, and then a height of minus 12. So here we have the clay, and here we have the sand. And we can assign materials already now, although what I am ultimately going to do, I'm going to subject this to a horizontal load at the top here of the pile, and so I only actually need to deal with half the problem. So I'm going to cut the other half away. Let's see, like that, and then I can basically cut this. And I didn't get the pile. Okay. That should take care of the... I didn't get the pile still. Okay, let's start from the beginning. Let's start from the beginning and then do it in a slightly different way. I'll start from here, make this box, and then make sure it's tall enough to base... The hell? Oh, okay, I understand. So, box should of course start on the ground, let's say -20. And then it always looks a bit sometimes strange. It's and then up like that. Now we have it. Okay, so here's half the problem. Good, and we can then assign materials. So I'm going to put some sand here, medium sand MC. I'm not sure, but that's probably not too bad. And then the clay, we can do two different things. We can, or there's sort of different possibilities with respect to the material point model. We're going to do two things here. We're first going to use a basic Tresca model. So that requires an undrained shear strength, SU, and that is the profile we have here. And I have put that into an Excel spreadsheet here, the coordinates from 0 at the top to -12 at the bottom. And I am going then to read this data in. You have to close this before you read it into Optum. That's how Windows works. So let's take that profile, import it, select the file, and it's the Cutoff profile, and here are the data. You could also link directly to the data file, but what I've done here, since I don't have that much data, I've just imported it. I think that, okay. Let's do it again. Okay, great. So that's the profile. The unit weight, we could set it equal to 10. We can do the same here actually for the sand. And the pile then, the pile itself is a hollow pile. So before we do anything, we need to basically delete the interior. This is of course not an interior, this is actually the soil here as well. So we've deleted the interior now, and we can delete the faces then, and then we can see that we have this kind of a hollow pile to which we then assign shell elements. So if I hide this one first, then we can select, I am going to then turn this one, select all the faces, the top face as well, and then apply a shell element. Now this is a rigid shell, so that is the kind of material model, shell material model relevant for ultimate capacity, provided of course the pile itself doesn't exceed its capacity. So we assume that's not the case. Otherwise we could have used a rigid plastic shell. That's also a possibility. Let's just remove those and remove feature shell, remove that one, shell, and then somehow this one disappeared as well. So for the shell element underground, we have something, we have to make some decisions with respect to the interfaces, and what we need to decide is what kind of reduction in strength should we have, what underend shear strength do we have at the interfaces as a fraction of the soil strength, and also importantly, do we have a tension cutoff? And we should definitely have a tension cutoff, and the way we handle that is by basically defining a new material. I'll call that Tresca Basic IF interface, and I'll make it a sort of a bright green color so we can see. And then I select all the shell elements underground, just the faces, and then I assign this Tresca IF material. We could also then, in addition, reduce the underend shear strength at the interface. So reduce the tensile, or set the tensile strength equal to 0, and in addition reduce the shear strength. We're not going to do that. I think in this paper they are, in another paper they mentioned that they don't do that, so we won't do it either, although we could. And this interface material here is of course the Tresca that we've just duplicated, and then we need to set the cutoff to yes please. Great. That's pretty much it. Then loads and boundary conditions. Standard fixities, it's what applies to the solids in this case, and then the shells, we need basically we need to have symmetry BCs for those as well. So that's a plate BC. I always like to work in global coordinates so then I can see exactly what's going on. So we need to support it in the Y direction only. The other two directions it's free. We need to constrain it against rotation as well, and also we don't allow for any rotation about this line up here. So all the translations are free, and then the rotation is fixed. And then applying a force or a load of some sort, what I would actually like to do is apply a point load right here at the center of the pile. And before I can do that, I need to have a point, so I need to define a line. I'm going to do that from the edge of the shell and to this point here. I have now cut the shell into two, and I can apply a load here at the center. I multiply a point load, and it is in the X direction. Remember, we are actually only applying half the load, so if we want the multiplier to represent the total load, well then we apply only half the load here to half the problem. And we're now ready to go. Oops, this was a radius of 1 meter, so I think this is kind of a bit more stubby than the piles that were tested, but nevertheless, let's see what happens. Let's use some mesh adaptivity as well. So it has apparently a capacity of about 3 meganewtons. mesh doesn't look very impressive, but experience tells us that this is probably not a bad solution. Only the solids are shown here in the picture. So this is basically how it behaves, and you can see clearly the effects definitely of the tension cutoff. Let's try to get some, we can do some strains, why not? Some shear strains. And that looks kind of like that. You already sort of see a familiar picture even for this kind of coarse mesh. And of course you can use as many elements as you want. So that's one possibility. Another possibility that I'd like to just mention is to use the so-called AUS model. So this is a model that was developed within Optum, and it's a kind of an advanced Tresca model where you have the possibility to specify both an undrained shear strength and compression, and then the undrained shear strength and extension as well, or the extension to compression strength as sort of a number. And quite often, not to say pretty much all of the time, the extension undrained shear strength is quite a bit smaller than the compression undrained shear strength. So this might not be a bad idea to consider this possibility. And so we again load the data for the Cowden data for the undrained shear strength and compression, and then in the extension the default value is 0.6. That might be a bit low. Something more normal would be probably something like 0.7. So let's try that and see what the effect of that is, and we apply that to the soil domain. Is now the AUS, and we then also need an AUS interface. And let's make that a bright color as well. And tension cutoff, yes. Hide that. Select only faces. And then let's have the AUS. So we now have the same strength in compression, but only 70% of the strength in extension of what we had before. And there's also another thing with this AUS model. It's going to be published soon after a very long struggle with more than one journal. This model is going to be published. So there's the flow rule as well. So one thing is a different strength and extension and compression, but the AUS model also uses a much more reasonable flow rule than the flow rule associated with the Tresca criterion. So basically the AUS model uses a von Mises criterion, or von Mises circle, you could say, as the flow potential, and that is a lot more in line with what you actually see in experiments. The Tresca criterion is not good for strength, but it's absolutely even more, if possible, terrible as a plastic potential. It basically implies that there's no intermediate principal strains between extension and compression, and that's obviously in clear contrast to what you see experimentally. So just a sec here. Yeah, I'll have to take this later. We're almost done as well. So the flow rule and the extension compression issue, their business, is what differentiates the AUS model from the Tresca model. And the AUS model is a lot more reasonable, and it gives lower capacities. That's sort of the effect of these two things: a lower extension strength, and then also a more reasonable flow rule. So here we are, 2.7 meganewtons versus I think we had 3.1 before. Yeah, so somewhat of a drop in capacity, and qualitatively speaking, things look pretty similar to what they did before. Strains possibly are a little bit different. No, not really. So it's the same kind of picture as we had before, but with a lower capacity. So that's it. There's the possibility, of course, also of doing a elastoplastic load displacement analysis, and I'll return to that in another video. See you next time.